Hi and Assalamualaikum everybody. We meet again. This is lecture 04 and in this video I'm going to cover several subtopics like the second law of thermodynamics, heat engine, refrigerator, heat pump and also energy conversion efficiency. Without any further ado, let us look at the first subtopic for this video. Introduction to the second law of thermodynamics. In the previous video, we have learned about the first law of thermodynamics in which it will be applied in the closed system and also the open system. But there is restriction in the first law of thermodynamics in which the first law of thermodynamics only highlights that the energy can change its form from one type to another type. But by only satisfying the first law of thermodynamics, we cannot ensure that the process can actually occur. So, I give you one example. We have a cup of hot tea in a table. When we leave it for a long time, that tea will not become hot anymore because of the heat will be transferred from the tea into the surrounding. From this example, we can see that the heat will be transferred into the surrounding spontaneously. But can you imagine the heat that already being transferred into the surrounding? Can it reverse back? Yes, that's a good question, right? So, that is why the only first law of thermodynamics to explain the energy is not adequate. Thus, in order to complement this first law of thermodynamics, it should be remedied by the second law of thermodynamics, in which the second law of thermodynamics stated that the processes will proceed in a certain direction but not in a reverse or in any direction. So we go back to the hot tea example. The heat will be transferred to the surrounding only but will not happen in reverse, which is impossible that heat that being released into the surrounding that will reverse back into that hot tea so that the tea can be hot again. That's why we need this second law of thermodynamics to remedy the first law of thermodynamics. So, from the first law and also the second law of thermodynamics, a process will be occurred by satisfying both first law and also the second law of thermodynamics. But have you ever think that can we reverse back this spontaneous process? Yes, of course, but it requires an external force to reverse the process. So, what is the external force? We will see in the next subtopic. So I give you another example. If let's say we switch on our fan and the fan will rotate, we can see here the electricity energy will be converted into the mechanical energy. But not all the electricity energy will be converted into the mechanical energy. It will be released into the surrounding in a form of heat. And this surrounding we call it as the thermal reservoir, in which this thermal reservoir will allow any amount of heat transferred from or to the system without having the temperature change. So that's the use of the thermal reservoir. Next, we go to heat engine. Just like I mentioned to you before, that we cannot reverse back the process unless we have an external force. Same goes to this example. We have work and we have also heat, in which from work, it will be converted into heat spontaneously. But in order to transform back from heat to work, it will happen unspontaneously. We look at this figure. From work, which is one form of energy, it will converted into another form of energy, which is heat, and this heat will be released to the surrounding. But in order to get this heat back into this system, it will not happen spontaneously. It will happen unnaturally. How? By using this external force or special device in order to convert back this heat into work. So, one of the device that can convert heat back into work, we call it as heat engine. So heat engine is a device that produces work from heat in a cyclic process. And the closest example of this heat engine is what we learned in the laboratory, which is steam plant. So what you have learned from the lab about the steam plant, so this is actually the flow chart of the steam plant. So in this steam plant, we are going to need fluid, and this fluid is the medium to channel the heat throughout this steam plant for processes to happen. So let us look one by one. in the steam plant, we have boiler, turbine, condenser, and also pump. So it started from boiler, in which this boiler will receive some amount of heat in order to transform from liquid water into steam. Next, the steam produced from the boiler will be channeled into turbine, in which the heat energy will be transformed or converted into work. But just like I mentioned to you just now, if we have this amount of heat, it will not totally converted into work. There are some of the heat that will be released into the surrounding or the reservoir. So that is why we can see here some amount of steam that is not converted into work. It will be channeled into the condenser, and this condenser will release the heat into the surrounding, which is the thermal reservoir. And then after the heat will be released to the surrounding, this steam in the form of vapor will be changed into the liquid phase, in which the liquid phase will be pumped back into the boiler. And this pump is actually to ensure that this steam plant will happen in cycle. In order to observe the performance of a heat engine, it can be measured through its efficiency, in which the efficiency can be defined from this equation, which is desired output over required input. And this thermal efficiency equation can be applied into this heat engine, in which the thermal efficiency for heat engine is equal to net work output over total heat input, in which this net work output is the work produced from the turbine, and the total heat input is the heat needed in the boiler in order to convert the water in liquid form into the vapor. So then, if we simplify the equation, it will become the thermal efficiency for heat engine is equal to W net out over Q in. The normal efficiency of a heat engine is lower than 1 or 100%. Just like I mentioned to you before this, the second law of thermodynamics will complement the first law of thermodynamics. So even though this heat engine, it applies more on the second law of thermodynamics, but the calculation of the thermal efficiency, we should start with the first law of thermodynamics equation, in which QH is equal to QL plus W net out. So how can we get this equation? So we look at this figure. So in any question regarding the heat engine, we should draw this figure for us to understand the direction of energy exerted or produced from the heat engine. Just like this figure, we can see that the QH, the direction will go into the heat engine, and QH is actually the energy coming from the high temperature reservoir, and it will be labeled as QH. Then the heat engine will produce work, in which the direction of work will be coming out from this heat engine, and there are some amount of heat that will be released or wasted into the surrounding, in which it will be labeled as QL. So that is why we can see here the direction of QL will be coming out from the heat engine. So if you look inside this heat engine, there are 4 shapes that represent the boiler, turbine, the condenser, and also pump. And we can see here, this boiler will receive heat in order to change the water in liquid form into the superheated vapor. Next, this shape is actually the condenser, in which some amount of heat that will not converted into work, it will be released into the surrounding or the thermal reservoir. And the thermal reservoir is the low temperature reservoir. So the temperature at the high temperature reservoir will labeled as TH, and for low temperature reservoir temperature, we will labeled as TL. Next, after we rearrange, we will get W net out is equal to QH minus QL. And this QH minus QL, we substitute into the thermal efficiency for heat engine equation, then we will get QH minus QL over QH, in which the Q in is actually QH. The Q that coming into the heat engine is QH, so that is why the Q in is QH. So lastly, we can rearrange until we get 1 minus QL over QH. So in order to calculate the thermal efficiency for a heat engine, we can use this equation. Next, there is this statement from Kelvin Planck that is highlight the principle regarding the thermal efficiency of heat engine. So Kelvin Planck state that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. It means that if, let's say, the heat channeled from the boiler into the turbine, not all the heat energy will be converted into work, and some of them will be released into the surrounding. So it means that this Kelvin Planck will strengthen the fact that the thermal efficiency of a heat engine will not achieve 100%, or the thermal efficiency should less than 100% because of the remaining of the energy will be transferred into the surrounding or the thermal reservoir. Next, we go to refrigerator and heat pump. Basically, refrigerator and heat pump are the same device, but the only difference for both of these devices is their function. So let us look one by one, the refrigerator and also the heat pump. So the refrigerator is a device to maintain the refrigerated space at low temperature. So this refrigerated space will be maintained at temperature by using an external work. So this refrigerator will extract the heat from the cold space and channel it into the hot reservoir. But for heat pump, this device is going to be used to maintain the heated space at high temperature by extracting out the heat from the cold space into a hot reservoir. So basically, the principle for these devices are similar, but the objective is different. So this figure is showing to you the flow inside the refrigerator and also the heat pump. Same as heat engine, there are 4 devices inside the refrigerator or heat pump, which are condenser, compressor, evaporator, and also the expansion valve. And one of the biggest difference from the heat engine is the work. For heat engine, it will produce work, but for refrigerator or heat pump, it's gonna need work from outside. For heat engine, the direction of QH will be going into the system, but for refrigerator or heat pump, the QH direction will be going out. So same goes to QL. In heat engine, the QL is going out, but in this heat pump or refrigerator, the QL is going into the system. It is crucial for you to remember the direction of QH, QL, and also work, and you should know how to differentiate between the heat engine and also the refrigerator or heat pump. So this is the comparison between the refrigerator and also the heat pump. And we can see that the direction of QH, QL, and also W for both devices are similar. We can see here for refrigerator, the direction for QH is going out, so same as the heat pump, it is going out. For QL, for refrigerator, it is going in. Same goes to heat pump, the QL direction is going in. And both refrigerator and also heat pump is going to need work from outside. And the only difference between this refrigerator and also heat pump is the objective. If heat engine, we can observe the performance through the thermal efficiency, but for refrigerator and also heat pump, we can observe the performance through the coefficient of performance. So the COP for refrigerator and also heat pump is different. We go first to refrigerator. The COP for refrigerator is equal to desired result over required input, in which it can be simplified into COP refrigerator is equal to QL over W net in. Means that the desired result for refrigerator is the QL, in which in refrigerator we are expecting that this amount of heat will be extracted out from the cold reservoir or the cold space. It is over the required input, means that how many work that is needed in order to extract out this QL. So the COP for refrigerator is equal to QL over W net in. Same as heat engine, we should apply the first law of thermodynamics to calculate the COP. So from the first law of thermodynamics, we can get W net in is equal to QH minus QL. If we go back in here, we should measure what is coming in is equal to what is coming out. So from here we can see that W net in plus QL, which is input, is equal to output, which is QH. So that's why we get this first law of thermodynamics, which is QL plus W net in is equal to QH. And we can rearrange, we will get W net in is equal to QH minus QL. And this W net in, we can substitute into the COP equation. And after we rearrange, we will get 1 over QH over QL minus 1. So the higher the COP, the higher the performance of the refrigerator. Next, we go to heat pump. So in order to calculate the COP for heat pump, we start with this equation, which is the desired output is equal to the required input. So the desired output for heat pump is the QH. The required input is W net in. So means that we are going to measure how much work is needed in order to maintain the temperature. So that's how we get the COP for heat pump, which is QH over W net in. Just like refrigerator, by using first law of thermodynamics, we will get the relation of the energy coming in is equal to the energy that is coming out. So we will get QL plus W net in is equal to QH. Then after we rearrange, we will get W net in is equal to QH minus QL. Then we substitute into the COP equation for heat pump. Then after rearrange, we will get 1 over 1 minus QL over QH. So if let's say both refrigerator and also heat pump are working together, so how can we relate? Is by using this equation, in which the COP for heat pump is equal to COP for refrigerator plus 1. This table shows to you the comparison of coefficient of performance between refrigerator and also heat pump. So for COP refrigerator, the equation is QL over W net in, but for heat pump, the COP is QH over W net in. And also after we substitute the first law of thermodynamics equation into the COP, the difference between the refrigerator and also heat pump can be highlighted here, right? And also if the refrigerator and also heat pump are working together, we can relate the COP for both devices by using this equation, which is COP heat pump is equal to COP refrigerator plus 1. So there is one statement which is from Clausius. It stated its understanding in this refrigerator and also heat pump through this statement. If we look from this statement, we can see that usually heat will be transferred into the area that has high amount of heat into the area that is low amount of heat. But for refrigerator and also heat pump, we can see that it happens oppositely, in which heat will be transferred out from the cold space into the hot space. So I think that's all for this lecture video, and the next video we will cover on the continuation of the second law of thermodynamics. So till we meet again in the next video, thank you and Assalamualaikum.